Hi there. Welcome to lecture 1 of this course on classical mechanics. This lecture is going to be about Newton's laws of motion themselves and will be the precursor to everything else that we do in the course. Now, I think a lot of students, when encountering a subject that's as old as this, think that even though Newton wrote down his laws all that time ago, probably we've modernized them in some important way that means that what Newton wrote down is not that relevant. I actually encourage you, maybe not now, but at some point in your physics career, to go back and read the laws as Newton wrote them. You'll find that they're strikingly modern. Newton was a pretty smart guy and actually did quite a lot to formalize the theory in a way that's pretty explicable to us today. So I want to start with Newton's theory as he understood it, or as I believe he understood it, and move on from there. Now, before we can actually talk about Newton's laws, we need to talk about the kind of space, the setting in which the theory happens. Newton's laws have, Newton's theory, I should say, is set in a world with two kind of entities in it. There's space itself, and then there are objects. And objects in the at least most basic version of the theory are all simply point-like and have mass. Okay, so what is space? Space is going to be some real vector space. So I'll say space is r to the d, where d is the dimension. Now, of course, we live in three-dimensional space, but sometimes it can be interesting to think about other spaces, and sometimes it's actually very useful to be able to imagine what's going on in a 2D plane that lives in 3D, or in a 1D line that lives in 3D. So we'll just consider the d-dimensional case in general. And then, as I said, we have objects. We can also use the term bodies. This was the term that Newton used. The Latin word corpus is what you find very often in the Principia. Or masses. And these have mass and sometimes other properties, like charge, or perhaps they are the source for a force. But in any case, with just these two entities, it turns out that we can explain quite a lot of phenomena. Whether or not we're facing left or right, or up or down, physics ought to be the same. It doesn't depend on the coordinate system that we put on things. It also, in at least the Newtonian theory, doesn't change if I start running that way. All the physics ought to be the same, but I'll need a different description of it. This gives birth to the notion of reference frames. Now, reference frames aren't actually found in Newton, but it's a concept that's embedded in the theory even from the start. And so I think it makes sense to start off by discussing reference frames. All right, so a reference frame we'll say is a set. So here's a definition. A reference frame is a set of axes for RD that may be moving, or maybe I can just say maybe changing over time. And here the idea is basically this. Imagine we start in some given reference frame. So that reference frame will have an origin, and it will have a set of axes that we can arbitrarily call x, y, and z if we live in 3 dimensions. Then any other reference frame can be described by a different set of axes, which are possibly moving with respect to the first set and also maybe rotated or something else. Now, I've already a little bit jumped the gun, but this immediately spurs us to thinking about changes of reference frame. So when we change a reference frame, what properties should we always want? We definitely need to preserve two things. The first is angles between vectors. If I get two of my markers here, if I put these at some angle and then I start moving them, or I rotate my head, or I turn the markers with respect to me, well, in all of those cases, the angle between them ought to stay exactly the same. And so angles between rays need to stay the same in Newtonian physics. The second thing is distances. I can do the exact same trick again. If I put these two markers at some distance and I start moving myself, or if I rotate my body, it always stays the same distance. Those of you whose physics curriculum has already covered special relativity will note that, in fact, neither of these statements remains true when we're talking about special relativity, but they're definitely true in Newtonian physics. And they're a good guide as to what transformations in reference frames can happen. So now we've written down a lot of words. Let's try and put some mathematical symbols on the board. All right, so we want a transformation T. So we're going to call our inertial transformation, or our reference frame transformation T. And T is going to send, well, it's going to send all the points in RD to other points in RD. But it has to satisfy these two properties. As it turns out, point number 2 actually implies point number 1. If we preserve the distance between any 2 points in RD, we necessarily preserve the angles between points. So how would we write this? We want, so with, I am still visible, okay, good. T of R 1 minus T of R2, distance, so I'll put my distance markers, is equal to the distance between R1 and R2. All right, this gets into an important point, which is the notation that I'm going to use for vectors in this class. So I'm going to end up using Newton's notation for derivatives, which involves writing dots above variables. Because I'll be writing dots above variables, the notation gets very cumbersome if I also use vector arrows on top of vectors. So many people working with Newton's notation also use underbars for vectors. So this R with a bar under it is vector R. It should make sense once we get into it, but if that's new to you, that's what I mean here. All right, so it turns out that transformations of this type are called Euclidean transformations. And although I won't show a proof here, it turns out Euclidean transformations have to take an extremely simple form. So a Euclidean transformation is always of the form, the transformation on R is equal to some matrix, which I'll call R, unfortunately. Now, in our underbar notation, I'll put 2 bars under matrices. So we'll have a matrix R operating on the vector R, and then we can add a constant vector C. And that's the only thing that we are allowed to do. But we do need to notice something. Which is that we can have these change over time. So a transformation between reference frames is given by a a list of that matrix at every single time and a list of that vector at every single time. So for all, so let's say T in the reals. Great. All right. So now we've just formalized exactly what was over here with this little bit of extra mathematical sort of machinery that allows us to say what these transformations are allowed to look like. All right, let's look at maybe the very simplest possibility. What happens if we have no C and R? So here, let's just do a bunch of examples. So here's one. We have T of R is equal to just R of R, and this is a constant. Well, this represents every vector just being, and of course, I've forgotten an extremely important point. Not all matrices are allowed here. The only matrices which are allowed are rotation matrices. A rotation matrix is exactly what you think of it as. A rotation matrix fixes the length of this vector R. All right. Now we can proceed. So actually, let's make a little bit of a note here, just so that it's actually on the board. All right. So in this case, all that this represents is that every vector in our space is going to be rotated about the origin by some amount. All right, let's try another one. Another possibility is, what if we just added C to every vector? Well, this represents all the points in our space just shifting by some constant. So because C is a constant here, it doesn't depend on time. That represents just a translation. So I can write here, this one is rotation. This one is translation. And it turns out that if I do some rotation and some translation, but both are constant, that actually represents maybe rotating about a different axis. Or you could think of it as a rotation and then a translation, or a translation and then a rotation. Either way works. Now, another example that's slightly more complicated. What if we have R constant, but C not constant? In particular, let's let C be a linear function of time. Okay. In that case, we'll have the following. So a linear function is going to just take the form something like AT plus B, where A and B are vectors. All right. Now, you can show, and it doesn't take too much to do so, that what this represents is a reference frame moving with respect to the original reference frame. And it's moving at a constant speed. Now, ignore the rotation for a second. Just imagine that this is the identity for a moment, because this only represents changing the axis, or changing the rotation of the axes before we do this translation. So if this is the identity, then what this tells us is first, just shift by a constant b. So from the get-go, just shift by b. After that, for every 1 second, let's say, or 1 unit of time, shift by another a. That represents the origin moving from b at time t equals 0 to b plus a at time t equals 1, and b plus 2a at time t equals 2, and so on and so forth. So really, this represents the one reference frame moving at a constant speed with respect to the other. Now, notice that 1 and 2 are actually just special cases of 3, right? So 1 is the special case when both a and b are 0. 2 is the special case when this matrix R is the identity matrix. And when C is, or I should say B is the constant C and A is 0. So all 3 of these are of type 3. So I'll say anything of type 3 is called an inertial transformation. Okay, an inertial transformation, again, is just one in which the origin is moving at a constant rate with constant speed, or I should say constant velocity, with respect to the old origin. So then the origin in the new reference frame is moving at a constant rate with respect to the origin in the old reference frame. Wonderful. Now let's continue with, let's say, two more examples. Now, first, let's imagine that rather than having r be constant, let's let it be a linear function. So here, I guess r can be the linear function, or sorry, the constant matrix A times T times the original R. And then we'll ignore any sort of translation C. So this is a non-inertial transformation precisely because we see that R depends on T, and that's not allowed in inertial transformations. R, this matrix, has to be a constant. So this is a non-inertial transformation. I'll just say non-inert. And in particular, it represents the axes rotating at a constant rate with respect to the original axes in the old reference frame. So this is like constant rotation. All right, and then let's do 5. So another possibility, am I still visible down here? Yeah, great. Is we have r, but now instead of adding a linear function, let's add a quadratic function. So we can say 1/2 at squared plus bt plus c, where now a and b and c have to be constants. So because this is a quadratic function and not a linear function, this is also a non-inertial transformation. Now, non-inertial transformations are very interesting, but they won't be the focus of at least the beginning part of this course. The reason we'll see later is that inertial transformations have special properties when we start talking about Newton's laws. So keep in mind that inertial transformations are at our disposal for the time being. All right, with that and with the definition of a reference frame, I think we're ready to start talking about Newton's laws. I'm going to clean up the board and then we'll be right back. Okay, it's time to discuss Newton's laws. And before we even get into this, I hate to break it to you, but Newton's laws are actually an outstanding area of controversy among historians and scholars of science. I am not a Newton scholar myself, and so I've done a lot of reading, but I could be wrong about any of this stuff. I encourage you as physics students to take very seriously the hard work that people in other disciplines do to understand this stuff and read them if you're interested. I'll link some stuff in the description that might be of interest to a select few of you. In any case, Newton's laws were stated at first in Principia, Newton's large tome on classical physics, in the 1680s, or at least the first edition. And Newton's laws actually appear not first in the Principia. He begins by listing some other things like definitions and some propositions. But they're the sort of main attraction of the first volume. Now, I want to take Newton's laws very seriously because I think that they present a really good formulation of classical physics for us to start from. To do that, I've gone and translated them from the Principia myself. So anyone with any issues with my translations should take it up in the comments, but it's not the fault of some poor translator. Before we begin the laws, I actually think that there is a necessary proposition that isn't stated in Newton, but is sort of implicitly there in a couple of places in the Principia where Newton discusses certain topics that require this. I'll put a little bit more on this in the description as well. So I'm going to call this the 0th law. It isn't the same as what other authors have called the 0th law, but nonetheless, I'm going to use this terminology. And that's just that Newton's laws apply in all reference frames. Now, this is the first place that I'm going to disagree with the textbook author. Taylor suggests that Newton's laws only apply in specific reference frames, but I think that this formulation makes a lot more sense. It's a lot closer to the text, in my opinion, and we'll see that it works just as well. All right, on to the first law. Now, the first law concerns what Newton would have called the principle of inertia, and its goal is to define natural motion. So, before the 17th century, many authors thought that motion might occur for a great many different reasons. Perhaps some objects naturally sought to be in a particular location, like objects made of earth sought to be near the center of the earth. Objects that are made of certain kinds of matter sought to be nearer to the heavens. Newton says that is not true. And he's following here from actually Descartes, who came up with a similar principle of inertia about 20 years earlier. And this principle is simply that objects try to stay going in a straight line unless they are impeded or acted upon by something else. And we'll see what that something else is in a moment. Okay, so in English, the law is everybody continues in the same state in which it is at rest or moving uniformly in a straight line except insofar as it is driven to change that state by impressed forces. Now, many authors seem very confused about the first law. Some have argued that it's redundant because the second law, as we'll see in a moment, tells us how large the acceleration is from a given force. And in particular, if the force is zero, then the acceleration is also zero. And so they would say, doesn't that imply the same thing as the first law, namely that if there is no force, then there is no acceleration? And no, it doesn't. Of course it doesn't. Because if there were other things in the universe than forces which caused motion, namely some sort of inherent property in an object, like its amount of earth or its etherealness or whatever, then simply knowing the forces wouldn't tell you the acceleration. And so that is not a reasonable interpretation of the first law. The second thing that some authors think, and this is Taylor's position, is that the first law seeks to define so-called inertial reference frames, which we're going to talk about in a little bit. This is certainly historically impossible because Newton didn't use the term inertial reference frames. That actually only came about in the 19th century. So let's leave it at that. I think my position is that it is simply a statement of natural motion, of what objects want to do, to put that in heavy quotation marks, if nothing else is happening to them, namely there are no impressed forces. All right, great. Let's move on to the second law. I think this one is maybe the most straightforward. Now, I'm going to write down Newton's translation, but then we'll discuss why I think that we still should give it a little bit of an update. So here's a direct translation of the second law. The change of motion is proportional to the motive force impressed and is made along the straight line in which that force is impressed. Now, a critical historical thing to notice is that Newton also invented calculus, along with Leibniz, it is now believed. But Newton's version of calculus, fluxions, he felt was not at a state of readiness to use in the Principia. So the Principia doesn't use calculus at all. That said, this second law is supposed to be true for a small amount of change and a sort of small. That said, the second law is then supposed to be true only for a small amount of time. So, and therefore a small change in motion. So we could actually just make this a lot more precise using calculus. There is actually one thing that I'm also going to change here, just because we're going to revisit in a few lectures Newton's actual statement here. But by motion, Newton probably means what we would now call momentum, or possibly what we now call impulse. But in any case, he doesn't mean acceleration. I'm going to restate this in terms of acceleration, and then we'll revisit the momentum formulation a little bit later in the course. So here's the direct. Here's a modernization. The second derivative of position with respect to time is proportional to the force. And maybe I should say, second derivative of the position of an object with respect to time is proportional to the force impressed on that object. Great. I feel like this modernization preserves the spirit of the direct translation, but also adds in this notion of second derivative that we get from calculus. All right, one more thing that's really interesting about Newton's formulation of the second law is that it doesn't make any reference to the mass at all. There's some indication that Newton thinks that this is an empirical question, or perhaps it's because he thinks about motion, which is related to momentum. But in any event, we're certainly free to add that m in as an empirical constant of proportionality. And I think oftentimes when we state Newton's second law in problems, we'll write it in the conventional form with which we're all familiar, F equals ma. Great. Okay, the third law. I'm going to write it out and then we'll discuss. All right, so a direct translation of Newton's third law is, to an action there is always an opposite and equal reaction, or the actions of two bodies on each other mutually are always equal and directed in opposite directions. All right, so the first thing that jumps out at us from the third law is that everywhere else in the laws, Newton keeps using this term impressed force, in Latin vis impressa. And he doesn't use that here. He uses the term action, which he doesn't define in the definitions. And so we're left to wonder what an action might be. My guess is, since he didn't put it in the definition, he means something sort of like what a layperson would imagine. And that is that an action of one thing on another thing is, the action of this thing pushing on this thing. And so an action is specifically a force caused by one object on another. And that allows us to clarify the, I think, a little bit opaque language in the third law. In this second part, it's not super clear what is acting on what. And so I think a good restatement of that second part is, if an object A acts on object B with a certain force, then object B acts on object A with a force that is equal but in the opposite direction. All right, the last thing to notice about the third law is that Newton doesn't say that all forces are caused by objects. And so he leaves open the possibility that there can be forces which are not caused by objects and therefore do not follow the third law, because there wouldn't be an action of A on B such that B could cause an action back on A. Actually, I want to step in here with a little bit of a historical corrective. And that's because I think physicists can often be eager to give too much credence to great man narratives that set brilliant geniuses center stage and imagine that they made, leaps of innovation without really relying on anybody else. That wasn't Newton's evaluation of his own content here. So, as I mentioned before, the first law appears before Newton in Descartes' work, about 20 or 30 years before, in fact. And the second law, Newton also thinks is not particularly new. He says that Galileo, Descartes, and Huygens have all looked at this before. In fact, Newton's evaluation was that the third law was his only real unique contribution that wasn't just a reformulation of what everyone else had done. Newton also understood that he was doing a huge project of formalization of what everyone before him had done. And that's an important part of the scientific process, too. So I really just want to take a second to appreciate that Newton didn't see himself as a singular genius, even if sometimes we're too prone to. Now, throughout the 17th century, physicists were more or less obsessed with figuring out what forces were. And that includes the Principia. Newton spends a lot of the propositions and definitions before the laws talking about different types of forces and what they might mean. So I think it's not that surprising that forces are a very confusing concept to undergraduates. And I think at the crux of it is that we have an equation in Newton's second law, F equals ma. But this only tells us the quantitative relationship between a force and an acceleration. It doesn't tell us the conceptual relationship between the force and the acceleration. Namely, is a force a category of thing that exists out there which causes the acceleration to happen, or is the force simply a descriptor for the right-hand side of the equation, m times a? Let's list these as two possibilities. So force as cause, that's the first possibility. And force as descriptor, that's the second possibility. Is this the wrong pen? So in the first hand, let's imagine that we take the force as cause possibility most seriously. I think this seems the most natural, right? We have things like the force of me pushing on this board, and I'm moving it, right? I feel like the force that I'm exerting is a cause of what happens to the board. Seems to have no issue. However, Newton's laws apply in all reference frames, and forces, we'll see, change as we change reference frames. Let's just state a really simple example. So suppose that in reference frame A, we have the origin stationary and the ordinary x, y, z axes. And in reference frame B, so the transition or the transformation, I should say, that takes us from A to B takes R, let's say in A, to, well, there will be no rotation. We don't need to worry about that. It'll just be RA plus 1/2 AT squared, where A is a vector. And as you might imagine, A represents the acceleration of the origin of reference frame B with respect to reference frame A. Now, let's suppose that we have an object at RA, a constant position in reference frame A. Then where is that object in reference frame B? It's right here. So now let's think about what happens. Well, actually, first, let's rewrite RA is then equal to RB minus 1/2 AT squared, since this represents RB. In other words, all I'm doing in this second line is rewriting it to solve for RA. Now let's take the second derivative. So if we have an object with some trajectory over time, then the second derivative of that trajectory with respect to time, again, I'm going to use Newton's notation here, where we say second derivative by putting 2 dots above the vector, and we would say first derivative by putting 1 dot above the vector. In any case, the second derivative of this trajectory with respect to time is equal to the second derivative of RB with respect to time minus the second derivative of the quantity 1/2 AT squared. But a simple calculation shows that that is just the vector A. So in other words, if this object has acceleration R a double dot in reference frame A, it has a different acceleration in reference frame B. But we know that this is equal to the force in reference frame A over m, and this is equal to the force in reference frame B over m. So therefore, Fa over m is equal to Fb over m minus A. And this is huge because it means that the forces are not the same in the two reference frames. They're different by this constant vector A, or I should say m times A. So if a force is something that causes motion, well, that's a little bit weird because as we change reference frames, a thing that exists and is able to cause other things in the world can vanish, it can change, it can do all manner of things. So maybe that leads us to reference frame, or not to reference frame, to conceptual possibility B here, that force is just a descriptor. We just say F equals MA, and all we mean by that is something like what we mean when we say the job took 30 person hours. We don't believe that person hours are a conceptual category that exists out there in the world. We know that person is a conceptual category, or persons, and we know that hours, or time, is a conceptual category as well. And we're mathematically allowed to multiply those quantities together to get a third quantity, person hours. But we don't think of the person hours as causing something. Perhaps person hours are just useful in some calculation that we're doing, and so we choose to multiply two quantities together to get the other one. But that just seems wrong, right? I mean, we have acceleration due to gravity. That gravity seems to be causing things, or the example I gave before where I can push on the board and it seems to move due to something that I did. So how do we escape the fact that neither of these possibilities seems to capture the whole picture? The answer actually is not too complicated. All we need to do is take forces and divide them into two categories. The first are real forces, and the second are apparent forces. So real forces, what are they exactly? Well, they're forces whose source we believe we know. So things like pushing. If I push on something, that's a real force. I'm exerting that push on the other thing. Gravity. The electric and magnetic forces, I should say. Spring forces. In fact, most of the forces that you might think of from a course on introductory mechanics are real forces. What about apparent forces? Well, those are going to be forces that in some sense are just remnants of the description of motion that we chose to use. And often they come when we take non-inertial transformations of other reference frames, as we saw here. A good example that you may have encountered in introductory mechanics is centrifugal force. Now, we won't deal with apparent forces very much in this course, and not until the end. But it's really important to note that if you're in a reference frame that has an apparent force, you do experience it the same as you would experience a real force. There's no way that you can tell just by experiencing the force whether or not it's real or apparent. And so we might think that we have an empiricism problem. But perhaps by some combination of experiments in different reference frames, we might come to believe that some forces are these real type. We know how springs work, or we know how gravity works. I won't be super clear about what we're talking about, only because we're going to almost exclusively talk about real forces. But it's important to note that this is a sort of interesting place to make a distinction. Now, we're going to use this to get on to talking about inertial reference frames, which are a topic that's covered in the book, and so I want to make sure that we get to. All right, building on the dichotomy we just drew between real forces and apparent forces, let's now give our own definition of inertial reference frames. So, what is an inertial reference frame? An inertial reference frame is one with only real forces. So it's certainly possible that an inertial reference frame exists. We start out in some reference frame. Perhaps we find that some of the forces present in that reference frame aren't real. So we do a transformation of reference frames. And that may eliminate the apparent forces, since, as we saw before, the forces can change between reference frames. Now, say that we do start in an inertial reference frame. We want to make a couple of statements that tell us what kinds of transformations we're allowed to do that preserve there only being real forces. In other words, that take us from inertial reference frame to another inertial reference frame. So, okay, let's suppose that we start in a reference frame that has only real forces. In other words, an inertial reference frame. And we do an inertial transformation. I'll abbreviate inertial reference frame IRF. Well, we know that the inertial transformation will have the form T of R is equal to matrix R of R plus C. And in fact, let's say plus, I think I used B here before, or AT plus B here. Let me use V to remember that this is a velocity plus C. All right. Now, just like we did before, let's give the name A to our original inertial reference frame. And let's say that the new reference frame is a reference frame B. So now let's invert this to solve for RA. All right. Well, in one step, we can subtract a bunch of stuff over. So this tells us that matrix R times RA is equal to RB minus VT minus C. And now we need to multiply by the inverse of this rotation matrix on the left. Now you might wonder, do rotation matrices always have inverses? And in fact, they always do, so we're always okay. Great. Now, just like before, we know that all of the forces in reference frame A are real. So if we have an object with a particular trajectory, and that we call that trajectory RA of t, then we can take its second derivative, multiply by mass, and we'll get the forces. So let's do that. We're going to multiply by mass and take two time derivatives of both sides. So this will give us m times RA double dot is equal to m R matrix inverse. Now this is a constant, and even though it's a matrix, a time derivative will go through it. You can prove this to yourself relatively easily by just writing this out using components. So write out what the components of the resulting vector would be if you multiplied the matrix out. All right, I'm going to continue. So RB double dot, and of t, I'll include these for the time being, minus, well, just like before, the time derivatives go through this matrix and, in fact, this vector. And all we're left is taking a second time derivative of a linear function. But the second time derivative of a linear function is 0. And so we're left with mr double dot A is equal to mr matrix inverse r double dot B. Well, this is equal to R inverse. Well, I should say, actually, this implies that FA is equal to R matrix inverse If I move this m on the inside, because it's a scalar, it can go past a matrix no problem, I get R matrix inverse times FB. All right, so we went from whatever the real forces were in reference frame A to the real forces or to forces in reference frame B, but which are rotated. So in other words, the relationship between the forces in A and the forces in B is just a rotation. We'll consider a force to stay real as long as it's just experiencing a constant rotation between reference frames. In other words, the force vector stays like this, but we rotated our head a certain constant amount. As long as our head isn't moving over time by a different amount of angle, then it's okay, we're still in the same situation. All right, so we've shown now that an inertial transformation on an inertial reference frame, and let me fill this in, takes us to another inertial reference frame. So this is great. It means that if we start in an inertial reference frame, we can get to other inertial reference frames by inertial transformations. And actually, this is kind of key. It means that as long as we only ever take inertial transformations, we never have to worry about apparent forces at all. We'll see that sometimes that actually isn't desirable. Sometimes we would rather worry about the apparent forces in order to work in a certain specific reference frame. But for the whole first part of this course, we'd rather do this. We'd rather ignore apparent forces altogether. This actually brings us to a really important point, one that I think is sort of foundational to a lot of the modern thinking about classical physics. Note that this suggests that a Newtonian universe does not have a well-defined origin, because we can always just take an inertial transformation to a system with a different origin, but that has the same forces, and so in some sense is fundamentally the same. Additionally, it says that there's never a sense in which there's a specific reference frame that's stationary, because we can always move to another reference frame that's moving at a constant velocity with respect to the first that has the same forces, and so in some sense is fundamentally the same. This principle is called Galilean relativity. And Galilean relativity is a very important kind of symmetry that we expect classical systems to have. So I think it's important to point out here. Now, we're going to finish off by just talking about the structure of the theory of classical mechanics. Now, I'm actually going to start us off here with this story. In 1684, the English astronomer Edmund Halley went to go and visit Isaac Newton in Cambridge, and he asked him two questions. He was interested in particular about the orbits of planets, and he asked, first, given knowledge of the trajectory of a body in space, can we say what the forces on the body are? And second, given the knowledge of the forces on the body, can we figure out its trajectory? Now, the story has sort of an amusing resolution. Newton says immediately, in answer to Halley's question about the orbits of planets specifically, that he knows the trajectory of a planet around a body, and it's an ellipse. Halley is somewhat surprised by this because it's a novel result, and he asks Newton if he will show him the proof at once. Newton, however, going to look through his papers, finds that he has too many of them and they're too disorganized, and he can't find the proof. But he promises Halley that he'll get it to him soon. However, Newton does not at any point respond to Halley with the proof. Instead, his new proof that he starts writing right afterward starts to balloon and balloon and balloon until it becomes the first draft of the Principia, which is published in 1687. So in some sense, these two questions, Halley's questions, form the foundation of modern classical physics. Now, to Halley's first question, from the trajectory, can we get the force? The modern student has knowledge of calculus, and so the modern student says, absolutely no problem. What I'll do is I'll take the trajectory and I'll take its second derivative. No problem. I'll multiply it by its mass, and I'll have mass times acceleration. That will give me the force. And so we have the force from the trajectory. However, the second question, from the forces on an object, can we get the trajectory? We can now give a more precise meaning to. First, we fix a reference frame. We state whatever real forces we know to be there, and we assume, for the time being at least, that there are no apparent forces, that we're in an inertial reference frame. Now we can ask the question, given those knowledge of the real forces on an object, can we predict its trajectory over time? So in other words, if we know this side of the equation, can we find this side of the equation? And of course, the answer is yes. The answer is yes because of the theory of second order ordinary differential equations, which states the following. If we have a second order differential equation like this, and we assume certain nice properties of the trajectory, which I'll allow you to look up in a math book, and we assume that we know the starting position and velocity of our object, then we can solve, or at least in principle, a solution exists for the trajectory at all points in time, both before the time that we start and after the time that we start. So we can both predict and retrodict the entire trajectory of the object. So use second order ODE, ordinary differential equation, uniqueness and existence theorems. Now, the main theorem that we're interested in here is called the Picard-Lindelöf theorem. You can look it up if you're super interested in that kind of thing. But for our purposes, it's enough to know that for a solution to exist, what we need is the set of forces, in other words, the left-hand side of the equation plus the masses, and then also the set of initial conditions. So really what we can solve are not ordinary differential equations, but so-called initial value problems. And this tells us what kind of theory we're dealing with. We're dealing with a kind of theory that's called a deterministic dynamical theory. Now, deterministic only means that the laws of physics in classical physics don't depend on randomness in any way. So even though we might not know everything about a system, if we did know everything about a system, we could determine its trajectory exactly. Dynamical here means the following. The system has a space of states. At the beginning of the video, we talked about the setting of classical physics and how we have objects and they live in a vector space, Rd. That vector space should not be confused with the space of possible states. Now, we imagine that we have n objects in d dimensions. That means that a list of those objects' positions lives in R to the d times n. So I'll say nd, because we need to list n d-dimensional vectors. No problem. However, a list of positions is actually not enough to determine a state. And why not? Certainly, if we took a snapshot of the universe at some point in time, that's what we would see. Well, the reason that we shouldn't consider a list of positions to be a state is because it doesn't give us enough to solve for trajectories based on this argument that we gave up here. Instead, we need both a list of positions for all of the objects and a list of velocities for all of the objects. So in other words, we need to take this number of vectors and double it. That gives us a single vector, if we want to think about it in that way, in R to the 2 times n times d, where n is the number of objects and d is the dimension. And I'll just put here that what we need is the positions and velocities. All right, the next thing that we need in a dynamical theory is a dynamical rule. This tells us, given the state at some point in time, what will be the state at a further points in time. And I should say that this all actually implies that we have a thing called time. So in this dynamical theory, time is a continuous variable that goes both forward and backward, in principle, both to infinity in both directions. In any case, the dynamical rule tells us, given the state, what will be its past and future trajectory. And that's exactly Newton's second law for us. So this is the structure of the theory. And in fact, knowing this kind of structure is what we're going to encounter gives you some sense of actually what most physics classes will cover. Dynamical theories are principally what we're interested in E&M and quantum mechanics, except for when we're measuring things. And really the only time when you don't see dynamical theories are when you deal with theories of optimization or control, which you'll hopefully cover in other physics classes. In any event, answering that second question from Hallie is going to be our preoccupation for the remainder of the course. We're going to do it in a lot of different ways and using a lot of different machinery, but fundamentally that's always what's there. Thank you so much for listening, and I hope to see you in the next one.